Testing. 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 All right. You're live. So we're going to try a slightly different format for this live stream and or listening. Today we're going to be looking at a Twitter thread. So this is a Twitter thread by Karol Hausman, who's a researcher at Google and adjunct professor at Stanford. First, we're gonna look at side of the street. So I had I actually briefly worked with Karol while I was at Brain, and he's a very good researcher. And he made a good point here that The Bitter Lesson by Richard Sutton, which we're going to get into here, is one of the most insightful essays on AI development in the last decade. Recently, given our progress in robotics, I've been trying to predict what the next bitter lesson will be in robotics and how we can prevent it today. Let me explain. So, Bitter Lesson by Richard Sutton. I think it's actually older than 2019. I think he's kind of been saying this type of stuff since the 70s, but I guess this particular one is 2019. But roughly what Sutton was saying is that if you look at computation and AI approaches over the years, it turns out that all we're really doing is waiting for the computers to 10x. Right? That at the end of the day, if you actually look at where you get these step function improvements, it's not through the designing of some clever algorithm or the discovery of some novel method. It's really not the algorithms and the methods. It's almost entirely the scale, where the way he puts it is that general methods that leverage computation, right, are ultimately the most effective and by a large margin. So general methods that leverage computation, what he's trying to say is it's not complicated algorithms and these complicated pipelines with 10 different steps and, you know, even just what we were looking at yesterday, like spherical harmonics and all this like kind of math that has all this theoretical background. It's simple ideas like gradient descent and then a huge amount of computation, right? And I think in his time, right, he was someone who did a lot of research in the 70s and the 80s and the 90s. In the 70s and 80s and 90s, there was kind of this idea of expert systems, right? And one way to think about that is you basically write a giant if-else statement that encompasses every single thing that can possibly happen, and then that's how you're going to get AGI, is basically one giant if-else statement, right? And people legitimately thought that these expert systems would be the road to AGI, and it turns out they were garbage. But so he kind of saw this in his time, how like over time, actually the ones that ended up performing best were the ones that could actually use huge amounts of computation. One thing that should be learned from the bitter lesson is the power of general purpose methods, of methods that continue to scale with increased computation even as the available computation becomes very great. The two methods that seem to scale arbitrarily in this way are search and learning. The second general point to be learned from the bitter lesson is that the actual contents of minds are tremendously, irredeemably complex. We should stop trying to find simple ways to think about the contents of minds, such as simple ways to think about space, objects, multiple agents, or symmetries. All these are part of an arbitrary, intrinsically complex outside world. They are not what should be built in, as their complexity is endless. Instead, we should build in only the meta methods that can find and capture this arbitrary complexity. We want agents that can discover like we can, not which contain what we have discovered. So this is the original bitter lesson, right? Where, hey, we're just kind of sitting around waiting for the GPUs to get faster, and that's how we're really going to make all these things faster. Okay, so that's a little background a bit on the bitter lesson, and this is actually a picture of Rich Sutton himself standing in front of a server mainframe, and in this meme, you have this person here who's kind of rage crying, and they're like, no, you can't just scale up pure connectionist models on blah, 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 and they're like kind of getting upset that the just using a ton of GPUs and a ton of scale and general computation, general methods that leverage huge computation is working the best, and Rich Sutton is here just laughing like, ha ha ha, it's all about just GPUs. So Karol goes ahead to say here, let's revisit the original bitter lesson first. The bitter lesson can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. The ultimate reason for this is Moore's law. The reasoning goes like this. We don't know how to build general purpose AI yet, but we know we'll need a lot of compute. We can recognize a trend outside the field. Computation is getting cheaper. Let's work on AI methods that leverage that trend. So let's look at robotics now. It is well understood that the biggest bottleneck in robotics is the lack of data. There is no internet scale data set of robot actions, right? If you're doing robotics research, especially AI-based robotics research where you're using deep learning, you have to collect your own data set every time for your specific problem, and the sense of being extremely time consuming, and you're always limited by the number of robots, so you're never really going to collect a data set that's on the scale of something that GPT is trained on, right? These big AI models, they can scrape the entire internet and train on that. In fact, let's assume it is impossible to generate enough data needed for general purpose robots using robots alone. Insufficient data. I think the name of this character in Star Trek, which is where this is from, is called Data. So we want to find something else that can provide the data for robots. In other words, we want robot learning to ride the wave of progress in other areas that will feed in more data to robots. We don't know how to build general purpose robots yet, but we know that they will require a lot of data. Trend outside robotics. Work on robot learning methods that leverage that trend. And Karol calls this the bitter lesson 2.0, which is a robotics version of the original bitter lesson. To prevent learning this lesson in hindsight, let's try to predict what the trend in 2 is, right? So what is the trend that robotics should follow? We're looking for a trend that is outside of robotics, like Moore's law was happening outside of AI, that will bring more data into robotics. Given the recent progress in AI, I propose the trend to be foundation models. So foundation models is basically GPT, DALL-E. It's just these giant models that are basically trained on huge amounts of data scraped from the internet and then trained for hundreds and hundreds and hundreds of hours on hundreds and hundreds of GPUs, where the training budget is like literally millions of dollars. So there's a huge interest in value in foundation models outside of robotics. They scale with data and compute, and then they are getting better at understanding the world. So you see here, there is a trend. Over time, you have the different types of models here. You have language, vision, generative models. They're called drawing here for some reason. And then you have the years down here, right? And you can see how this y-axis is actually a log plot. So it's 1, 10 to the 4th, 10 to the 8th, 10 to the 12th, and so on. And you can actually see how the models are just getting exponentially faster or exponentially bigger, right? Palm, GPT-3, Lambda, Palm has 540 billion parameters. GPT-4 has 1 trillion or something. If we think of foundation models as distilled internet-scale datasets, assuming that we can leverage them into robotics, they will provide a ton of data so that robots so desperately need to understand around them. So distilled internet-scale datasets. What does that mean? Is that you might not have the dataset itself, right? The internet-scale dataset might not be available to you, but in a sense, the foundation model, or GPT, is that data set, right? You can basically query it and it'll kind of interpolate whatever you're giving you and give you the kind of interpolation within that data set. So in a way, the model is just a proxy for the data set. So Karol here is saying, to summarize, I believe that the next bitter lesson in 70 years will be the biggest lesson that can be read from 70 years of research is that the generative methods are ultimately the most effective. The next longer thread, I'll present some examples of how we try to leverage this insight into our robotics work. And we're working on way more research direction. Okay. Here's the next thread. So this is some of the research that Karol and his group have done at Brain that kind of leverages the foundational models that we have available right now. So started here. Few examples on robotics that leverage bitter lesson 2. Say can, we showed how we can connect robot learning pipelines to large language models, bringing a lot of common sense knowledge to robotics. The hope was that LLMs become better, which they seem to be constantly doing. It will have a net positive effect on robotics. LLMs, again, large language models, and then say can, I think is specific work that was done on this robot. So Google has a little robot. It basically looks like a little Roomba, and it has an arm on it and has a little head on it. Right, here you go. Here's a little arm. But you can see how basically the operator asked it kind of a relatively text-based question, right? I spilled my Coke on the table. How would you throw it away and bring me something to help clean? So that's kind of the command is in natural language. And then the robot is kind of creating this list of tasks here. Go to the trash can, put down the Coke can, bring it to you, find a sponge, pick up the sponge. So it's kind of creating a, I guess, a set of plans or an action. I haven't actually read this paper, but Robotics at Google, everyday robots. What is this? We're building a new type of robot. Okay, so this is actually the robots that I was talking about at Google. So I guess they're maybe spinning it off into a company. I would assume it's its own thing. It looks like maybe it's its own little spin-off company. And then Robotics at Google, the organization where I worked briefly, that is basically just a research org. Let's read the abstract for SayCan here. Large language models can encode a wealth of semantic knowledge about the world. Such knowledge could be, in principle, how can you math? So I think food station, maybe one thing you can look at is, I know that this guy, this is a book that I remember reading way back in the Deep Learning with Python book. So Deep Learning with Python by Francois Chalet. And then 3 blue, 1 brown. And then maybe playlists neural networks. There are two sources. So I think books are a little bit outdated, to be honest. I think in 2023, trying to learn deep learning from a book is trying to get better at cooking by reading a book. You kind of, that's not the way to get good at cooking. You kind of have to cook. So I think deep learning is the same thing. It's you're not going to learn as much by reading a book as you are as going to be a little bit more interactive. I think the YouTube videos list that I pasted there, I think that YouTube content creator does a really good job of having like kind of graphics, and it really gives you a more visual idea of what the statistics and the math are actually doing underneath. So I would take a look at that. Okay, let's get back into this. For example, asking a language model to describe how to clean a spill might result in a reasonable narrative, but it might not be applicable to a particular agent, such a robot. We propose to provide this grounding by means of pre-trained behaviors which are used to condition the model to propose natural language actions that are both feasible and contextually appropriate. The robot can thus act as the language model's hands and eyes, while the language model supplies high-level semantic task. We show how low-level tasks can be combined with large language models so that the language model provides this high-level knowledge about the procedures for performing complex and temporarily extended instructions. While value functions associated with these tasks provide the grounding necessary to connect this to a particular environment. Okay, so it seems like the data set that they're working with is basically they've somehow tied robotic action space, right, which is what joints are you sending to the controller or to the motors on the arm, with language space, text. So they've made that kind of mapping in their data set, and then they basically just use, yes, find an apple, find a Coke, pick up the apple. Okay, and you can see how it can do a bunch of different. It's basically just picking different objects, finding different objects, so on. So that's SECAN, which is using LLMs to control robots. In our updated paper, Palm SECAN, which I guess is just SECAN, but they use Palm, we indeed observed better lesson 2.0. Just by changing the LLM to a more performant Palm, we got better performance, chain of thought prompting, handling queries in other language. So in the original paper, they had some result, right? And then they took the LLM that they were using, the foundational model that does language completion, and they upgraded it to a slightly larger foundational model that does language completion, and everything else got better, right? Every part of the robotics got better. Very easy to incorporate new skills, leveraging chain of thought reasoning. So it's almost like they got a ton of new behavior for free, right? There is almost no performance drop on planning success rate when changing the queries from English to Chinese, French, and Spanish. So it literally, now it understands every single language. So this kind of really feeds into the bitter lesson 2.0 kind of narrative where, hey, actually the only thing you need to do is just kind of wait for these LLMs to get better. You're just waiting for this external scale to increase in order to improve your own micro problem. Second example is innermonologue.github, led by embodied reasoning through planning with language models. Recent works have shown the reasoning capabilities can be applied to domains beyond natural language processing, such as planning and interaction for robotics. These embodied problems require an agent to understand many semantic aspects of the world. LLMs planning and embodied environments need to consider not just what skills to do, but also how and when to do them. Answers that change over time in response to the agent's own choices. You can see here this little robot is, can you bring me a soda? The robot creates its own action, find a Coke, pick up the Coke. Action was not successful. I see an orange soda. There's no Coke, but there's an orange soda. Is that okay? And it says, no, please bring me a lime soda. It's kind of like creating its own actions. By leveraging environment feedback, LLMs are able to form an inner monologue that allows them to more richly process and plan in robotic control scenarios. And here we have like a kind of a pick and place kind of stacking task. In this case, VLMs, I guess, language models, bring a lot of non-robotic data into our system, allowing us to get better planning feedback mechanisms. With better LLMs, our system can continue to get better with any new robotic data. Better lesson 2.0. Another example is code as policies. So these are all works from kind of basically the same group. Right, these are all the same robot. Just variations of kind of pick and place. Capable of synthesizing simple Python programs from doc strings. These code writing LLMs can be repurposed to write robot policy code given natural language commands. Okay, so now you're using LLMs to just directly write Python code. That's kind of cool. Yeah, so you see, look at this. This code generated by a large language model here. And this is kind of like a handcrafted API here. So, I mean, someone has to make this name before, or make this API beforehand, but you can see how objects, fruit names, objects. Nice. Use a command, draw a hexagon, draw a line. Quite cool. They're directly using text or LLMs to basically program here. LLMs read your favorite robotics textbooks too. It's actually changed my thinking down what LLMs can do for robotics and what LLMs actually are. It's not just about allowing us to communicate with robots in natural language. As the LLMs get better, the robotics policies now will also get better. Policies is basically just the actual neural net that's deciding what action to take given an input. Released our code as policies robot demo using grad.io on Hugging Face. Need an OpenAI API key and codex access. Okay, so you can do it in a simulation, I guess. Finally, another example. We have Dial. Dial, also kind of the same thing, LLMs to robotics. So this seems to be kind of an explosion of work here. We have a lot of LLMs being applied to robotics to kind of not only give you natural language control, but then also it's helping the actual planning as well. Robotic model that can execute over 700 instructions at a 97%. So that's all in 2022. I'm optimistic that by riding the wave of progress in other fields leveraging data and disguise from foundational models, we can make significant progress. Okay, so we saw how basically Karol and the rest of the researchers here at Robotics at Google are kind of really seeing a step function improvement in what is capable with robots by using LLMs to do everything from interpreting the user action to designing the actual set of kind of the state machine that the robot goes through in terms of like which actions should I take, and then even just writing code directly for the robot. So this is exciting for sure, and I think to me this is actually huge because robotics has kind of been an unsolved problem for so long, and so many people have been doing research in robotics for so long, and it just never really got anywhere, right? You were just working on the same pick and place demos for decades, right? And now you're finally seeing like an actual step function improvement in the complexity of these pick and place demos that you can do, and you're also talking to these robots in natural language, which is huge. So to me, this means that this robot that they have at Brain, the robot that they probably have at Amazon, the Optimus Prime robot they have at Tesla, I think there actually is a path to success there, where there seems to be a path, like at least in maybe 4 years, 5 years, to a actual functional robot that's in your house and does what you want. So that's exciting. I think by 2030 we're actually going to have house robots, and it's not like in 2000 when we thought that by 2010 we'd have it, or in 2010 that we thought by 2020 we'd have it. I think right now in 2020, looking at the state of this stuff, I think by 2030 we are going to have robots in our house. But maybe to tie it all together and put a knot on all of this, I think it's important to remember that the reason we're going to have robots in the house has nothing to do with clever algorithms and clever formulations of pipelines and so on. The reason we're going to have that because large language models got better, because GPU. Yeah, so that's my thoughts on the Bitter Lesson 2.0 by Karol. Great thread. Great work from Google Brain. If you guys like this format, let me know. I can do it. Today I just didn't have a ton of time, so I had to do a kind of a quicker stream, and I thought that maybe I'd try kind of reading through a Twitter thread. But let me know if you guys like it, and thank you for listening.